Okay, so on to the next part of this series. If you remember in the last video, we derived the first order transfer function of our tank, gravity drained, and then we also did it in terms of series down below. And yeah, we did all that math after linearizing from the Taylor series expansion and then taking the Laplace transform. And then remember, we also did a little bit of I don't know, showing the work for those Laplace transforms. So that's all our work. Just kind of a recap. If you remember where we're coming from. Honestly, I feel like I can just copy. Uh, well, hopefully this is enough reference. I can draw some rough sketches, but we're basically doing the same thing. Um, well, we're not redoing it, but we're going to be coding it in Python. So take a look at our problem statement here. Now with our 3 tanks in series, we're adding an additional flow for our inlet in the second tank. So I can draw that out. And then we use the Jax.Jacobian. So that's another linearizing tool we're using to get these state space matrices. So this is what that is talking about. This is kind of coming from, or this is coming from the Wikipedia page. And I'll go into that in more depth uh, in a little bit. And then after we grab those sets of data, essentially, we'll be relating the third tank height to any changes in the inlet flow of, I believe we're doing the first tank. Oh, also the second tank. Okay. So I believe in class we only did the first tank, but I can also show an algebraic way to relate it to the second tank as well if we choose to change it as well. Um, yeah, and then comparing the linear and nonlinear responses. So as you might be able to guess, the linear response, since it's an approximation, will definitely be a little off from the nonlinear model that we normally use for this problem. I believe we did this already with, honestly, let me just go to the collab here. If you remember, we did this quite a bit ago. Did we even use, yeah, we used solve IVP. So it was also 3 tanks. And you'll realize, oh, well, I guess this doesn't actually show it, but doing it non-linearly this way actually does solve the problem, to be exact. But the way we're doing it is we're linearizing it in terms of these matrices. So again, these are, I took a screenshot of this and all down here, the transfer function. And the reason why we're doing this is, well, there's the, check out recording. Okay. Uh, do I want to talk about this now? Yeah, sure, why not? Um, so you might be able to guess, why are we trying to kind of ruin our exact solution from solve IVP when of step number 1 we're already linearizing it, our nonlinear model, into this state space representation where we have matrices that pretty much are linearizing the change of our variables, our inlets, and our, we call this state variable, our height in this case, on our right hand side, which is denoted by the x dot here, which is just which is the differential dh over dt in our case. So why are we doing that? And then also, why are we doing the Laplace again to get the transfer function? So again, everything comes back to this transfer function, and it's this idea that with the transfer function, there's been a lot of work and research into work. I guess I'm repeating myself, but the idea of transfer functions being used to do multitudes of things, and in our case for process control and dynamics, one of those is stability analysis, and I believe we'll be doing this later with the Baudet diagram. But essentially, maybe for an example to give something more tangible than just concepts, if you had something like an old car and a steering wheel, changing how obviously where it turns, and then maybe you even have some lag in between that control. Well, those two ideas of the lag and the way the steering wheel will adjust is part of that stability analysis. So maybe your control is however far you are deviating from the center of the road, and then you take your current position and you subtract it from the center of the road, and now that's your error. So in order to correct that error, normally we'd multiply by something like a proportional constant to correct for that error and make up for it, and then eventually veer back. But now you have this, well, usually you have a lag as well, and then you have to determine how much exactly are we going to what is the value for our proportional constant that we're going to use. And that boils down to the stability analysis. How aggressive do we want to be with that proportionality constant? Since maybe if you go to the very extreme, if you have a very high proportional constant, then think of this as the center of the road. You veer off a little bit to the side. Hopefully that caught onto my mic, but you veer off to a little bit to the side, and then you have to overcorrect aggressively to the other side. And then you kind of see this little wiggle, this I'm failing on to remember the name right now, but a sort of uh, function that keeps saying wiggles. I can't think of the word, but anyway, it keeps on overcorrecting itself. So this stability analysis is what allows us to determine exactly what value can we pick. So what is the limit of how aggressive that control can be? And then once we have that limit of from our stability analysis, we'll be able to, again, optimize that for a smoother control. So that's what we're going to be getting into. But let's focus on what we have on our problem here. So going back to our I guess my OneNote here. Let me go back to this screen. So yeah, I guess kind of makes sense to explain exactly what we're doing. So we have, again, this idea of a state space representation model with other fields of engineering. So this is chemical engineering, if you haven't noticed yet, like civil and aerospace, mechanical, those fields of engineering. They usually also talk about transfer functions, but they kind of view it from this respect of state space representation models and kind of working to interconvert like we're about to do right now. So focusing on this first line here, we have our, well, just reading it off, we have our right hand side, this right here, our x dot, that's denoted as, well, x dot shown here as a differential. So for us, this would be our change in height over change in time. So basically our right hand side. And we're saying that this is equal to some state matrix A and, or I guess I should be underlining, some state matrix A and some state variable X. So kind of going off to the side here, let's translate that in terms of what we know. And again, all of these are in terms of time. Let me write that out. I'll focus on these first two terms for now. So again, this is our change in height over change in time, our right-hand side, and this is our matrix. I'll keep it as an A. But for X, we have state variables. I believe it should be noted right here, or I guess a state vector. So it's a vector of our state variables. And again, it doesn't have to be one, but I'll be starting with a single tank, and then you can kind of see how it bridges off into a series of tanks. So in our case, 3 tanks. So this would be our heights, and of course that would change with time. And yeah, I mean, that's the most basic translation, but essentially what this is saying, well, you might be curious of what this A matrix is. So what does that mean? Well, if you have 3 heights, in our case for our 3 series, excuse me, this height would be 3 values. So this matrix has to be 3 rows in order to do that matrix multiplication. And essentially what this matrix is doing, I think you saw in the problem, it said Jax.Jacobian. So that's the determinant of our first order partial derivatives. It's taking the partial derivatives of our right-hand side, this dH dt, that, remember that equation? Well, I guess I can just go to it, honestly. Let's see. It boils down to, honestly, just this Q in minus Q out, but then we substitute the Q out. So we can just focus on this here. And then obviously, we divided by the AC here to the other side. Wow, that was horrible. But that's the equation that we're looking at when I'm talking about all of this. So going back to our notes here, essentially you're taking the partial derivative of that expression, so of our right-hand side, our dH dt, with respect to the state variable. So in our case, it's just height, so we're lucky it's just one variable, but you can imagine with many variables, this gets more complicated. So if you remember, one of our other problems we had was a tank with a reactor, so that would include concentration, temperature of the reaction, And if you had many reactors, maybe 20, so that's two state variables for 20 reactors, then you already have 40 state variables that you have to keep track of. And then trying to do that by hand with this partial derivatives of the our right-hand side, well, that just gets a little tricky. So this idea of a Jax-Jacobian is what allows us to automate that process. So I'll go into more of what that is later and how that relates, specifically the matrix. But again, this A matrix, we call it matrix A, is the dependence of our right-hand side, dHdt, on our state variable. So in our case, it would be how the change in height depends on the individual heights of the three tanks themselves. So again, moving on, we also have our B and U. So B and U denote the output, or I'm sorry, input variables. So in our case, this is the inlet flows, Q in, and B again being a dependence. Now, instead of a partial derivative for the state variables like A was, it is a partial derivative for, with respect to, I should say, with the inlet flows. So again, it's only one variable, so we're lucky, but it's actually pretty simple, since when we do the partial derivative, if we divide this expression by AC and then we isolate dHdt, well, if you take the partial derivative of that, everything else is essentially a constant, or we treat it as a constant because we're taking a partial derivative, and the partial derivative of the right-hand side ends up becoming 1 over AC, so 1 over the inlet flow. So nothing too bad, since it's just algebra at that point, or I guess, well, it's a derivative, so not really algebra, but simple math that we can keep track of. So don't be afraid of all these letters that kind of show up right now. So again, if I write out now the other side we had, this was B of t, our matrix, we call it, I think we call it input matrix, is that right? Yeah, input matrix, and then times our output, or I'm sorry, I keep saying output, input, so this would be input vectors instead of the state vectors. So relating this, we still have our B of t matrix, and then now it is the inlets, inlet flows that change. So this could be any number of inlet flows, and or it doesn't have to be inlet flows. It could be any input variables we put in. So going back to that example of a concentration, or I guess a reactor tanks in series, then you could have temperatures going in, you could have concentrations going in as well for each tank, and that could also mean the same thing. So you have two inputs for 20 tanks. Again, that's 40 inputs, that 40 values you're placing in your input vector, or input vector, right? Yeah, am I saying that right? Yeah, input vector, u. So there we go. And then of course, if you have five, let's say 5 inlet flows, so 5 values in our input vector, the B matrix has to be 5 columns, compensate. And if we keep the idea of 3 heights for 3 tanks, so we have 3 tanks, but now we have 5 inlets going in, the partial derivative has to still come from, am I saying that right? Yeah. So this is still 3 by 3, our right hand side. So our B matrix has to be 3 by 5 in order to make this equation make sense. So remember that we can't multiply matrices that don't have corresponding numbers like so. Oops. The columns of one matrix has to correspond with the rows of the other. So doing something like this, so we use at, remember, for our matrix multiplication. And you'll see this again when we do the Laplace transform. I guess I'll do an example for that as well. This is what you can actually do. So these are actually the same matrices. So this doesn't work, this does work. So keep that in mind when we're doing our matrix multiplications. And then now there's this idea of a output vector. We actually won't deal with that in this problem, or I don't think at all in this class, but essentially you might be confused in saying, well, if we have a state variable, isn't that our output variable? If we have something we're interested in knowing how it changes with our system, isn't that just the output that we're interested in? And the answer is not quite, since Remember, with transfer functions, these are being multiplied across several systems. So the output vectors are actually the state variables we want to carry over to the next system. So the next transfer function. Maybe an example could be if you have a moving object. So you have a state variable like position, and then of course the derivatives and second derivatives of position being velocity and acceleration correspondingly. Maybe you're only interested in the position, and of course let me add another state variable so it doesn't get confusing. So you have position and momentum as well, and now you only want to carry over the position of your system to the next transfer function. So you would have two state variables, position and momentum, and your output vector in that case would carry the variable, your state variable of just position. So that's a kind of quick example of trying to make sense of that. But again, we won't be using that in this problem. Take a drink here. Okay. I have a feeling this is going to be a long video. So yeah, we'll be focusing on just that equation so far. And then we have our transfer functions. And remember, when we do take the Laplace transform, we do this in terms of the deviation variable, in which case that allows us to essentially get rid of this term that appears after taking the Laplace of the differential. Remember, kind of showed that over here already. I believe it was just a quick aside right here. So we use the apostrophe, or I guess prime, to denote it was just h minus h bar, h minus the initial steady state. So deviation variables, or is it variables? I think it's, deviation variables. We do those subtracting the initial steady state. So when it is at steady state, it's essentially 0 when we take the Laplace. So this is pretty much what we did in the previous video. We take the Laplace of our equation mentioned before, and of course the differential simplifies to S, so the Laplace domain S times the Laplace of our state variable, and then the evaluation at 0 for our state variable is 0 since we're in deviation variables. And also, I guess this is a good point to point out, I guess. A and B, those matrices we talked about before, are now not functions of time. So notice that up here, there are functions of time. And now when we take the Laplace, they are not functions of time. So this kind of has to do with an idea of LTI. I believe it's linear time invariant. There you go. So linear being, again, that the idea of the Taylor series expansion around the steady state. We get one value. Well, in our case, for a single tank, it's one value. Well, actually, in all cases, it just evaluates to one value, since it's showing how our right-hand side depends on the corresponding variable. So for the A matrix, it's the state matrix. It'd be showing how the value, give me a value for how the height changes, in our case, how the heights of the individual tanks influence, I guess, the right-hand side dHdt. So this idea of linear time invariant. So time invariant being we're evaluating those Jacobian matrices at steady state. So we'll have a singular value for both A and B once we do the Laplace transform. So I believe that's all I want to talk about for this. Going back to our notes here. So we take the Laplace, and the A and B matrices are now LTI, linear time invariants, since we evaluate the Jacobians at steady state, and we factor out our, after grouping our, I guess, the Laplace of our state variables, we factor it out on the left-hand side, and notice there's this I term. So that I term comes from, since we're working with matrices, there's this idea of an identity matrix. So in algebraic terms, it's essentially 1, but we have to put this in when we're doing, I guess, I don't know if you can say algebra with matrices, but when we factor out a matrice from another matrice, we have to keep that one placeholder so that when we multiply it back in, it's still the same. So it's the same thing as I don't know. I think we did this in the last video, probably when we factored out, but maybe if we do something like 5x plus 3x, or maybe, I don't know, this is not a good example. So we use our Laplace, and then maybe we have a, let's just keep it s minus a, honestly. So algebraically, we know we can just multiply this back in. Well, obviously there's xa there. And I'm getting slow. Okay. So we know we can multiply it back in, distributive property and all, but we have to have a placeholder I for matrices, since matrix, I guess matrix multiplication is not commutative. So essentially it's just a placeholder. So I don't know if I'm over explaining that. Maybe I am, but just think of it as a one, and that'll be important. Again, the identity matrix, the definition is when we multiply the inverse of a matrix by the original matrix, that should give us the, well, it does give us the identity matrix. That's the definition. So again, this goes to 0. Remember, evaluating at 0, since we're in deviation variables. And after we factor out our state variable, we isolate it on the left-hand side. And of course, this term is 0 since we multiply across by, or I guess we're dividing across, but technically we multiply by the inverse. So think of the inverse as the reciprocal of a matrix. It's what allows us when we're doing something, I don't know if this is right, the right idea, but be like, so when we usually do algebraic manipulation, we divide by the same thing on both sides, so it cancels out. So this is what, essentially, is the same thing as what we're doing. Now I'm just making these up, but this reciprocal here is treated as an inverse in matrices. So we have to keep that in mind. And when we use Sympy, our algebraic, I don't know, symbolic, I should say symbolic solutions for, I mean, it's on the Python, so I'll probably say it again, but it's the symbolic solutions library we import for solving. I think we use integrals, derivatives, simultaneous equations, and for our case specifically here, matrices. So with Sympy, we'll have to do this reciprocal 1, and again, it's also denoted with a power to a -1. So that's what dividing it across means. Yeah. And all that boils down to is our transfer function right here. Since notice that now we have our state variable x is equal to our transfer function times our the Laplace. Well, all of this is in the Laplace domain, but we have our input. So I should include the Laplace domain there. So this transfer function is b over si minus a. And that takes the form of what we normally know as our, well, in our case, it won't be first order, but usually we see it in this form. So that's a transfer function. So that's what we'll be doing when we, all this state space variable stuff, and then back into transfer functions, and then we'll be comparing them on the plot once we, well, plot it up, I guess. So I guess it's worth doing a quick sketch of what we're doing. If you want to review the specifics, check out those previous videos. But since I'm already kind of going a little overkill on the explanation, I'll try to keep this quick. So we have 3 tanks. 3 tanks. Inlet flows going in. And I believe I said there was initial flow in the second tank. So this is 1, 2, 3. And then we have heights, height 1, height 2, height 3. I don't remember if we're interested in this outlet stream for height third tank, but I'll write it in. Then we have a couple inlet flows, Qn1 and Qn2. And we have the outlet flows, so I can number these Q1, 2, Q2, 3. And I believe that's all. And remember, with our outlet flows, I'll just generalize them like so. We had our whole of our, I don't know, whole of our tank times the velocity going out. And with Bernoulli's, we approximated that velocity as 2 times gravity times the height. So those heights correspond to the tanks and our overall equations. So I'll also generalize this. I think I'll need to write these out, so I'll write them all. I don't know. We'll see how it goes. So we had our differential times our cross-sectional area, and that was our change in volume. So dividing across, we had 1 over AC, and this was simply Q in minus Q out, dictating how that volume changed. And of course, we substitute Q out in here. And then we have our expressions relating our inlet flows and our heights. So that should be all. I don't think I need to draw anything else out. I'm hoping not to swap too much in between, but yeah, I guess I'll just see how it goes. My iPad side here. Hopefully it stays awake. But yeah, let's just jump right in. I'll keep these open. So I think I have these open as references. So this is actually the 3 tanks we use. I think this is one of the first videos we did. I'll just code it again. I don't feel like I should copy it. And then we had, I think, just a example for our root. We just took a parameter and a function, and then we had a guess for the single parameter. So root, we have to provide 1 parameter to guess, which we'll be using root. Then solve IVP is the non-linear side that we're comparing our linear side against our transfer function versus solve IVP essentially. And then remember the right hand side for solve IVP takes in 2 variables. I don't remember where I defined them. Maybe up here. Man, I don't remember where that was. Let's see. Where did you show up? Oh, right here. So we took in time as an independent variable and well, this is a vector of the dependent variable. So it takes 2 parameters. We'll be using lambda for root and solve IVP, I believe. Did I say that right? So we have, well, this is just our tank. So root and solve IVP. Since our right hand side, if you remember, will have 3 parameters. It'll have time, it'll have height, and the Qn. So we'll just do let me just run this off. Come in here a little bit. And yeah, so I have these variables set up for single tank, and I don't think they're written in the problem, but if you want to follow along, these are the variables I'm using. And then series tank, a little different, I think. Yeah, very well, just a little bit different. But with the series, we have to provide arrays for our guesses, and well, for our initial steady state, our guess here is needed later on. I think for our minimize, when we actually try to solve for the initial steady state, but I'm getting a little bit ahead of myself. But since I brought it up, we'll need to solve for the initial heights. We can do that by solving a root of our right hand side, since remember, for our initial steady state of the heights, that's essentially when the right hand side dH/dt is equal to 0. So we do a root solver on that, and we should be able to get our heights. So I think we have everything added. Just a quick aside, if you're using the template from our class, I think we forgot this line of code. If you try to use straight from the template, or if you're smart, you go off of his the code we wrote for the previous class. But in case you're using the template, make sure you have this line of code, or else when you do the symbolic imports and function calling, you'll have errors. So I found that out the hard way. So again, this template, we have JNP Jax, so we're going to be using the Jacobian. Remember, Jax is just the machine learning, equivalent for NumPy. And then Sympy, again, I brought this up before, symbolic solutions for integrations, derivatives, simultaneous equations, and in our case, matrices. That's the one we're using today. Plotly, that's how we're going to plot things, same thing as normal. And we've already discussed optimize and integrate from SciPy. We've done root before, we've done solve IBP before, and there's this minimize. So I believe in class we use minimize since we couldn't figure out how to use the root solver to converge. Since there was this issue with the root solver, it doesn't have bounds that it can limit it by, and minimize is just a function we can use that's just more robust, and it can actually evaluate roots at 0. So there's that with the bounds. But I actually found a guess that would work for roots, so I'll also show that. But essentially, it's kind of an additional step. But just in case we need it in the future, I'll show it anyway. So I don't know what that did. Okay, let's start with our single tank. So I don't know if we want to call this right-hand single maybe. So define our function. Why not? And we had our time. We had our, well, if it's just a single tank, we have 1 height and then 1 inlet. I'm kind of repeating our single tank that we did before. And we're defining our Q out as we normally do. We did, I think it's just, was it area of the whole? Yeah, area of the whole times, and I'll use JNP so the matrices work. So square root, remember JNP is equivalent, so we normally do NP square root, it's the same thing. So JNP square root, I believe 2 times G times H. And you can honestly just return, you know what, I'll show it all anyway. So normally have DHDT, we had that as 1 over AC, and we had Q in minus Q out. And I say return DHDT, and hopefully that works. Awesome. And now if we're solving for the initial steady state for the height. So to do that, we do a root on our right-hand side. But remember, root only needs 1 parameter to take a root of. So in this case, since we have 3 parameters, we need to provide a function that only has 1 of those, and the other 2 are essentially provided already. So to do that, this is a perfect place to use our lambda function. So we don't have to define another function just for this. So I'll say solve for the h of the following expression. Remember, lambda only takes 1 expression. And then I'll provide those variables as we need it. So 0 for time, since we don't really care about time. Height, I keep it as a variable since I still want to solve it. And I should say this is the single one. Height, since that's what we're solving for, and Qn. So we have a initial steady, I guess steady state, but initial value for that provided already. Again, these are all pretty arbitrary. I think I'm taking these straight from class, so if you're curious where that comes from, and then I believe we needed a guess, right? Yeah, x0. So I'm gonna give it a guess of say 1, and hopefully this should converge. Let's go, it does converge, and we have a number. But you'll see that if I try to provide a, does it work at 0? Actually, I'm not sure. It does converge at 0, so that's cool. If I provide a negative guess, which won't work since, yeah, it doesn't make good progress since we're going into negative square roots. Notice we have our square roots here of h taking, well, I guess in general, our root function here can't take a square root of a negative, but minimize can, surprisingly. So that's why, initially, why we chose to use minimize, but if you actually provided the correct guess, it'll actually converge. So we'll keep it like this since for our single tank, this is all we're concerned with. So after we have our, this is our initial height. So I'll say just initial height, and we grab the x attribute. Let's take a look at that just to make sure. This is our initial height. So remember, we're trying to get this in terms of state space representation. So to do that, we have to create these A and B matrices. I believe in the problem statement, it said Jax.Jacobian. Just turning off this. So with the Jax.Jacobian, Oh, we're at 30 minutes. Okay. um, for Jax.Jacobian, again, we're taking the partial derivatives of this right-hand side. So we defined our right-hand side as q in minus q out. And that was, if we substitute q out here, that's our entire expression. And we take the partial derivative with either respect to h, our state variable, so that's our A matrix, and with respect to our inlet flow, so that's our input vector u. So, and that's our B matrix. So, and start doing that. So Jax.Jacobian is line of code, and we say we want the function that we're taking the Jacobian of, so right-hand single, and we also provide which variable in this in the parameters are we trying to take the partial derivative of. So remember, indexing from Python starts at 0, so it goes 0, 1, 2. We want height for our matrix A, so we'll do 1, and that'll give us a Jacobian. So that's our A matrix. But notice that we don't actually have a value. It's just saying, wow, you have a function now that you can call and evaluate. So with that matrix, we'll evaluate it at the initial steady states, honestly. So I should put h0 here since we actually already solved for that. And qn0 is still the same. So those are our steady states that we're evaluating at. Now we have a number. So cool. And usually we combine these all into one line of code. Usually it's not separate. So we'll do that. And let's see how that looks like. Perfect. It's the exact same thing. Okay. Now we do the same thing for our B. Honestly, I can just copy paste this since there's not much change other than the fact that, well, it's a B matrix. This is our input matrix. So we do it with respect to instead of height. So it's 0, 1, 2. Q in is the third. So it goes 0, 1, 2. We put 2 here since that's the partial derivative we want to take it from. Our right-hand side with respect to our Q in, our input, and we evaluate it at the same steady state. So now we have a number, and this is 1 over AC. Remember, if I take the derivative of that function of our right-hand side, we have AH multiplied by, or I'm sorry, AC being divided by Q in, Q out. Q out divided by AC is a constant. We're interested in Q in, so the partial derivative of Q in over AC is just 1 over AC. So 1 over AC should give you the exact same number. Pretty cool. Now a little bit more on the A's and B's. So how does that, again, I mentioned that how the right-hand side changes with respect to their variables. So with the A matrix, I can just show you here. So obviously if I evaluate the right-hand side at our initial steady states, we should have an output of 0. So to the negative 15, essentially that's 0. So if we want to see this relationship between A and the right-hand side, so how does A show that with a single value? So if I add something like 0.23, and I also do multiply A by 0.23, we should have similar values. Yeah, pretty close. So 0.09.1, that's pretty close approximation considering A is just that linear, remember the slope, the Taylor series expansion, essentially linearization of the square root h. So those are how they're related. Go ahead, delete that, and I might just combine these all into one when we have to. Well, I'll be using this to copy paste so I don't have to do it again for the series. So now we have our state space representations. I don't even know where I am. So we'll be doing the transfer functions now that we have those. Notice that when I evaluated at the steady state, at the initial values for steady state, now our matrices are singular values. And remember that was part of the LTI, the linear time invariant. So now we take the Laplace transform of that, and essentially it boils down to what I wrote earlier. So essentially B over SI minus A. So the way we do that is by taking the reciprocal and multiplying by the inverse. Kind of an aside here to show if you've never seen matrix multiplication or algebra in general, say believe this is kind of like middle school math, but we had systems of equations where maybe it was like x plus y plus c equals some number, 1 maybe. Another set of equations, so 4x minus 5y, I'm making these up, 3z equal to 5 or 6 or whatever. And then, I don't know, 9x plus 5y minus 7z equal to 9, sure. And the way we represent that with matrices is something like we have our A matrix times, I don't know, solution. So I can just call this a solution, honestly. And then that is equal to our outputs on this other side. So maybe a B matrix. So the way I would represent that with the A matrix would be something like I'd create an array and put our list of variables. So for the first one, it's just ones. The second one, we have, so it's 4, -5, 3. And for our third set of equations, or just third equation, just 9, 5, and I can't type, 9, 5, and -7. Think of that, 1, 1, 1, 4, -5, 3, 9, 5, -7. Okay, so shift enter on that, look at that. So that's our 3 by 3. And we have our B matrix. So that's just an array of 3 numbers, 1, 6, and 9. 1, 6, and 9. Make sure we have our brackets. And then I'm going to reshape this so it matches the same shape of our A matrix. That way we can actually do the matrix multiplication of the inverse. So we reshape it into so I put a -1 here, so it says to reshape it into whatever values that I input it that correspond to the elements, and then 1 for one column, and we take a look at that. So it should be a 3 by 1. Perfect. I'll see. So why not? So this should be 3 by 3. I don't know why I see. Oh, shape. 3 by 3, and this should be a 3 by 1. So now that we can do a 3 by 3 times a 3 by 1, that should work when we do the inverse. So it's exactly what we need to do. So again, if we want to isolate our solution, normally we do b divided by a, right? That's for algebra. But in our case, we're doing matrices, so we have to multiply by the inverse on this side, and that basically equals 1. So if that's the case, when we do inverse times the original matrix times the solution, then we do that to the other side, inverse times b, we end up getting a solution is equal to a inverse matrix multiplication times b. So this is a 1. And you can see that when we do the inverse. So I'll call this the inverse. It's NP in algebra. I think it's just inverse. Yep. And of a, take a look at that. So this is the inverse of our matrix. If we multiply this by a, we get our identity matrix. So that's what I was talking about earlier with this I. So that identity matrix is 1 diagonals across and then zeros. Well, these are essentially zeros on the other sides. So that's how we do that's how we solve a matrix system, I believe. So we do something like this, we'll get our solution set. Oh, what did I do? Did I not do this right? Is it b times it? Oh, I'm sorry. Is it just b? There we go. That scared me. So take a look at that. These are solutions for x, y, and z for our corresponding equations. So that's an aside that took a couple minutes, but now you know how to do matrix multiplication, doing the inverse for all of that. So that's what we're going to be doing. So I'm going to be writing out just the second term. Remember, our x0 evaluated at 0 is 0 because we're in deviation variables, and our transfer function is just b over si minus a. So we have a, we have b, and we have, well, we know what I is now. It's the identity matrix. So if I start with, I believe it's already endpoint as S, right? Yeah, so this is Sympy. We do symbolic solutions. So we have our S times our identity matrix. So I think, is it just Sympy.I? Sympy. And in our case, we only have one value since we have one initial variable, not one state variable and one input. So the I matrix has to just be one. Remember when I was talking about if there are multiple variables, it becomes essentially, well, 3 heights becomes 3 by 3, 3 inlets becomes 3 by 3. So, well, that's not true. If it's 3 state variables and 3 inlets, then your B matrix is 3 by 3. But again, I already talked about that, so I'll avoid over explaining it. And then we have minus, what was it, SI minus A, right? SI minus A, and then we do reciprocal. So SI minus A. We have to do a matrix, so we do a Sympy.matrix, and I think it's capital M. So we import it as, not even in here. I think it's just a default, right? Yeah. So we do capital M, matrix A. So what that does, I think did I delete all my arrays? I can do an array of this, I guess. So if I do Sympy.matrix of that, does that become an array? There you go. Kind of shows it in a different font, showing it's like a different solution. Well, it's a symbolic solution, so that's all it does. It turns it into an array that looks like that. So whatever the variables are, it'll make it an array. So that's why we have to do the Sympy.matrix, and then we take the reciprocal, I believe, right? Reciprocal, and then multiply by B. So reciprocal, again, denoted with, it's pretty similar to how we normally do it. Why? Actually, yeah, the power of -1. Yeah, that's normally how you do it in algebra too. So Sympy does, syntax you need is 2 asterisks, so a power to -1. Then we multiply by B. So again, we do another Sympy matrix of B. And that's our transfer function. Oh, what did what is happening here? Oh, matrix multiplication. Oh my goodness. Can't believe I forgot the thing. Oh, that's not it. Is it the inverse of this? Or I'm sorry, -1 is the inverse. I don't know what I was saying, but I'm confusing myself. So S to I, A, B matrix A, that's right. The -1, that's our inverse. And we matrix multiplication. Okay. I don't know 1 and 1. I. The 3 by 3? Oh, is it still thinking of when I did A earlier? That'd be funny. Wow, it was. Okay, that's funny. So now that scared me. Man, okay. So remember, I use A for that example problem, so I just need to run it all again. Or I could have just run this again. But anyways, that's our transfer function. So pretty cool. All that work for our transfer function. And now we're going to be doing this again for series, but we're interested, well, now instead of a singular transfer function, it'll be, I think, a 2 by 3 or 3 by 2 matrix of transfer functions, and those correspond to our 2 inlets, and the rows being our heights. So I can write that out once it shows up. But yeah, I think we can just get started here. Honestly, I'm tempted to just copy paste these height. I think I think it shows that I know how to do this. You know what? I'll pull up the OneNote. Why not? Oh, do I? Yeah, sure. Okay. Where is my OneNote? Here. Right here. Yeah. So hopefully I don't screw this up somehow. Yeah, I'll copy paste what I wrote down. There you go. And instead of right hand side single, I'll just call it right hand side. So Now we'll have vectors of our heights, so we need to unpack that. So that'll be a height 1, height 2, and height 3. Qn will also be a vector, so that'll be Qn1 and Qn2 vectors. We have multiple of each component now, and now we have to write Q outs for all of them. No, Q out 1. Does that make sense? Sure, why not? So Q out 1 depends on height 1. Copy paste this. We do this 3 times for our outlet flows. Again, I'm just honestly increasing the number of it's a series, so we have to account for the fact that there's multiple tanks and there's multiple outlet flows and multiple inlet flows and multiple heights. So now we have, instead of just dh dt, we have the change in height. So this, I guess we can call this h maybe. So the change of heights for each tank. So dh1, and now this will be q out 1. And honestly, I think that's it. Copy paste. Gotta love doing the work already. So I just correspond the corresponding outlet flows to their tanks. But we do have to be careful here, since I don't think I showed it in the general form, which is pretty bad. But with the inlet flow, it's fine, since we only have one inlet flow, one outlet flow, looking at our one note on the side there. But for the second tank, you see we have a second inlet flow other than, so normally you have the outlet flow from the first tank being an inlet. So this is Qn1. Did I say that? Oh, I'm sorry, this is Qn1. I don't know what I'm doing. Qn1, Q out 1. And that's our outlet flow from the first tank as an inlet flow to our second tank. And we're taking out an outlet flow of our second tank. But we have to make sure we add our Qn2, that I think red arrow on the second tank right there to my left. Right? So my camera's flipped. So it's that Qn2 coming in. So that's another inlet flow we have to add. And I think that's it. Third tank is still Qn of, all right, this is a Q out 2. I don't know why I copy pasted. So this is Q out 3, 2. I don't know what I'm doing. Q out 2 is, yeah, Q out 2 is the outlet flow of the second tank and the inlet flow of the third tank. And then that we're taking out Q out 3. Okay. Heights correspond. We're doing J and P. Awesome. And then make sure we do our J and P array. So the reason why we're doing J and P is so it corresponds to our Jax.Jacobian. You'll get an error. And it fixes itself if you use J and P when you try to do Jacobians of our function here. So we'll do dh1, dh2, and dh3. Need to make sure I put brackets as well. Bang. These work. Okay. Now we do our roots. Okay, so here we go. Oh, I'll delete it. This is what I was talking about earlier when I was saying it would not converge. So in our case, it's just RHS. What is happening? So we're taking the roots of our series right-hand side now. I didn't label it. I just call it RHS to save some time. And now our initial guess and our steady state have to correspond to this series. So we have one defined already, and this is an arbitrary number, but we have initial steady states for our Qn. So that's an array. And X naught has to follow as well. We have to have an array. Did I have a guess for that? I did. Okay. So that should be 0.1. This, it didn't work with 10, I believe, last time. We can try it with 10. We'll see. That might be fine. So I'll put in guess here. And I think that's it. So we had our lambda, since root only does one parameter that is solving the root for, and then we had our function evaluating or evaluating the other parameters at their steady states. So time we didn't care about. Qn, we had an array that we made up here, and initial guess has to be an array, which we use 10. So 10 is actually very far off. It shouldn't converge, right? Because remember, we had 1 as our initial guess here. So if I do something like 0.1, try that. I think I can do times 3 here, no? Or will it yell at me? Oh, it works. Okay. Yeah, see how the convergence or the root does converge, and we should get the same numbers we get if we try to do minimize. So I'll call this I don't know, let's do H not steady state alternative. And we want the X attribute, and we'll go ahead and display that. And there we go. Those are our 3 heights. So you might be wondering what this was. Essentially, I'm multiplying by 3. It's the same thing as typing 0.1 3 times. So you see me do that again. That's all that there is to it. Remember, these were 3 tens. I simplified it to just 0.1 and multiplied by 3. So you do need 2 brackets here since you're tripling the value inside the bracket. Wow, we are at 1 hour. Okay. I'm glad we're on series though. Okay, so I'll do the minimize way we did in class. Now minimize is a bit different since there's a function that you have to, I guess, put in as a parameter. Oh, wow, I'm still in OneNote. Oops. Hopefully you saw all that. Okay. But anyway, minimize is, well, we have to have a function we're doing a minimize of, which in our case we don't. So we'll use our dummy function, our anonymous function lambda, and essentially just set that to 0. But what we're interested in is these bounds and constraints. Since notice that if I put 10, or remember earlier in our single tank, if I put in a negative number here, our root solver failed. So minimize is better in the case where, oh, it's more robust. It can take a square root of 0 actually, and it'll actually converge when we had a bad initial guess. In our case, we have a good initial guess. I guess we didn't care to try the changing our initial guesses, but we'll do it with minimize. We can try putting our bad guesses too, and it should converge to the exact same numbers here. So let's try that. Honestly, there's more parameters, but the ones we're interested, we'll be doing a function, our guess, so those aren't optional. So the guess being same guess we put in here. And I said I would put in the wrong guess, so maybe it's worth putting a wrong one here. Honestly, I'm just tempted to just, whatever, I'll do it. Wrong, maybe. H and then blah, 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 wrong. And then I'll put 10 in here. And I'll put that in our minimize, and oh, that's so bright. And so we have our function, so that's the same lambda. We're, all right, I'm sorry, lambda, we're not doing that. We're doing 0 for our function here. Since we're not minimizing an actual function, we're using the bounds and constraints, essentially just tricking minimize. So we can use these two. So if you go down here, bounds and constraints. So bounds uses, well, essentially just a range. We'll put brackets from 0 to infinity. Since that's what the heights can be, it should just be a positive number. And we can set it at 0 since minimize doesn't care. Remember, other times we use and ranges, we had to add or subtract a very small number so it didn't converge at a certain point and fail, or try evaluating at the point and fail. So normally we do something like 0 plus like 1 e to the negative 15, so like a very small number for the lower range, and same thing with the higher range. I think I did this for Panchon Savret, but moving on, we have our constraints, so we can have multiple constraints or a singular constraint, and that corresponds to a single dictionary or a list. And well, this is well, both of these are optional, but we're using them. And with these dictionaries, you have keywords we can call. One of them being a string for equality. So we're doing an equality so that it's not equal to 0, and the function is our constraint. Again, our lambda. And this is where we actually put our lambda, solving, essentially putting the root solver expression that we normally put in the root solver in our minimize here. And you have additional parameters here, but we're not worried about that. So enough explaining. Let's try and do this. So I'll do I'll do minimize for now. What is happening? Okay, minimize. Did I? Yeah, I did import it. Okay, so remember our lambda. I spell lambda. Our function, we're not actually minimizing anything, so it has to be 0. I can name this whatever I want. We had our guesses, and I said I would use the wrong guess for this one, just to see that it would converge anyway. And then we have I'll do constraints first. So we have constraints, and this was a dictionary, right? And then we have a keyword for our equality. Was it type? Syntax for this is very brand new. It looks, what am I doing? Type equals key, type equals EQ. So equality, and doing the function where that given constraint is applying to. So our function, and that's just our lambda right here. Trying to solve for that height. And then after that, we have our bounds. And now I'll do our fun little double bracket where it's 0 to NP infinity. And I'll multiply that by 3 since we have 3 tanks. So the bounds apply to all 3 tanks. And hopefully this converges. X0. I'm not too sure what this is. Let's see here. One dimension. Did I put multiple dimensions? Is this bracket changing it at all? Oh, yeah, I guess it was a bracket. I guess when you do an array, you only need one bracket. But it works if you put in root solver, apparently. Okay. Anyway, did converge, and looks like it is the same numbers here, 4.592. So I'll go ahead, put that in as our actual H naught steady state. No, what did we do for our QN? Initial steady state. So I'll do initial steady state, set that equal, and do our grab that X attribute, and I should actually call it so we can see it again. And here we go. Exact same. What do you know it? Even if I put any wrong guess in here, it still converges. So that's why minimize is stronger, more robust. And yeah, now that we have our initial heights, remember last time after that we did our Jacobians. So this is actually pretty straightforward as well. The only difference being now we have vectors and arrays. So instead of evaluating at one single values for the initial steady states, now we plug in our steady states, well, right here, and for our height and our Q initial. So I can do a multi-cursor H naught initial steady state and Q in, oops, that, and Q in as well, initial steady state. So hopefully this works. Oh man, what do we got? Q in initial steady state, Q in initial steady state. What's happening here? Oh, okay, let's see. Oh, we had JNP. We had our state 3. Have an array here. Still 3, 0, 1, 2, 1 and 2. This is a problem here. I've got incompatible shapes for block 2 and 3. Coming from the first line. All right, I'll pause here. Try to fix this. Found it pretty quick. It's not the right hand side single. Remember, we changed it to just the right hand side. So gotta remember when you're copy pasting, other things change. Awesome. So these are, instead of single values we had earlier for A and B, now our changes, our linearizations, those Taylor series expansions, are now vectors, or I'm sorry, not vectors, matrices, that show how each component of the variables respond to the inlet flows. And well, respond how, I'm sorry, I said that wrong. How the, well, for our A matrix, how the state variables are heights, the partial derivatives of those, how that influences our right-hand side, dHdt, and then how our inlet flows influence the right-hand side. Notice there's 0 here since we don't have a third input. So remember, it had to be 2 by 3 since 2, again, the columns were inputs, the number of input variables, and rows were from the state variables. So I think now we can do the transfer function. So we already did that as well. Pretty awesome. Go ahead and do that. Now we have a identity of 3. So we have to do 3 across since we have 3. Remember, this is coming from this identity matrix comes from our state variables, and we have 3 of those. So there's 3 diagonals across. Kind of notice from our A matrix matches up. It does. Is that it? I think that's it. Let's try it. Wow. Okay, here we go. So this is exactly what it's talking about. The transfer function is now an array of, I guess, can you call this a matrix? I'm not too sure. I think it's a matrix. So you have a matrix of our transfer functions that show the columns, 0 and 1. Remember, Python starts from indexing 0 and 1, so this is inlet 1 and inlet 2. And then the rows, you have 3 rows, so that's the height of tank 1, height of tank 2, height of tank 3. And I believe the problem statement, if I pull up my OneNote, iPad is turning off. That's not my OneNote. This one, here. We are interested in how the heights of the 3 tanks. Oh, heights of the 3 tanks to the inlet flows. Oh, we're only doing transfer functions? Oh no, here we go. Comparing the flows. Okay, well that's confusing. But I know in class we compared the height of the 3rd tank, so height of 3rd tank, 3rd row, how it changed with response to a inlet flow Q1. So that would be inlet flow Q1 here and height 3 here. So there'd be this indice for this array. If I go back, honestly, I'm tempted to just label it. Yeah, why not? Doesn't hurt. So take a screenshot of this, plop it in the OneNote, and I'll switch over to screen share and honestly just make a quick note of it. So again, this is index splicing 101. I don't know. So we have 0 and 1, Q in 1, Q in 2, the columns. And then we have, I should have given myself more room, but row 1, we have height 1, height 2, height 3. So our state variables. So if we're interested in the response of height 3 with Q1 input, we have to indices slice our transfer function. So we count from row to column. So 0, 1, 2, and then column 0. 0, 1, 2. Hopefully that makes sense. So this is height of 3 with respect to, or how it changes with, essentially, I could just do something like this. So how we have our height, 3rd tank, transfer function, multiplied by our Laplace of our Q in. And if you also wanted to see the influence of the 2nd inlet flow, you do the same thing. Make sure you indice at the correct one. So it'd be this transfer function instead. So that would be a 2, 1 times the inlet flow of 2. So that's how you would monitor the effects of each inlet flow with the height, and you'd add them together to get both of their influences on the height. So that was pretty quick, but just wanted to make that extremely sure that was the case. 5%, okay. What else are we doing? I think we just graphed this, no? So let me locate in the splice. I think we said 2, 0, right? So this is this transfer function, height 3, height of 3rd tank, and inlet of the first Q inlet, inlet flow. And we want to simulate this. So simulate is a simulation of our transfer function. I think this is already up here. Did I explain any of these? I don't think I did. So these are functions that our professor created for us that kind of more specifically are detailed to our class, and they're kind of coming from this signal library, SciPy.signal. So it's a signal processing library where communities have created many tools to, especially for our case, process controls and dynamics. And these are kind of more specific tools, kind of pulling from that library, but kind of changing the way slightly how they perform or function, so they're better suited to our class's needs. So simulation simulates a transfer function, PID, process, process? Man, I don't even remember. It's like integral derivative. Can't believe I can't remember what P is. That is not it. Oh God. Um, process integral. It is process, no? Proportional. Sorry about that. Proportional integral derivative. So we've done proportional integral before. No, I'm sorry. We've done proportional controllers before in I think it's this problem, right? So this offset with the error, and we multiply by KC our proportional gain. So forget that other PID. Google is super late, so forgive me on that. Transfer function, first order, second order, and then shift with any step function. We can shift our transfer function over so it's 0 before that time. So we'll be using simulate to simulate our transfer function. There's some default parameters, but we have to input our actual transfer function. So that's TF at 2, 0. Height of the tank, height of the third tank in response to inlet flow of the first inlet flow. And then U is our gain, or I guess our step change for our, remember U was our input vector. So we have to input some change for that. We can use lambda for this. Lambda U, and then maybe say we just have a step change of 1. And then the defaults, so this is 100 increments for step change of 0.1. So if we do shift enter, we should get times in increments of 0.1, 100 times. And well, these are all our height changes for the third tank. So maybe, I don't know, time. So time, and we're unpacking this array. So H3, I think we use height 3 deviation in class. So I'll do just that. Now we just plot this up. So figure one, so just make subplots. It's been a while. And then I'll do my update layout really quick. I should just copy paste this, honestly. Poly dark. So late. I'll add scatter my points. So we already have our X, which is time, and our Y, which is this height, third height, my words. The height of the third tank, how it deviates. So how it changes with time. And remember, this is a deviation variable. I won't add it now, but I'll add it when you can see it or see where it makes sense. I'll call this the linear. Yeah, see how that works. So yeah, it's our transfer function evaluated. Well, we're simulating our transfer function with a step gain of 1. So we changed it from steady state. Notice that I think it'll just be a constant if I do this, right? Yep, perfect. Since there's no step change, it's still at steady state. So we have that steady state. So there's a change now. Notice that, I guess are we not at steady state? Or deviation variables? Or I'm sorry, I have to add the steady state. That's why it's starting at 0. So you'll see it when it makes sense when I have to do solve IVP. We do the nonlinear version, and you'll see that our solve IVP nonlinear deviation, I guess, starts from our steady state, since that's what it is. It's starting from initial value. So I don't know, put it right here, maybe. We're so close. 114, not bad. Solve IVP. Remember, our function takes, solve IVP takes a function with independent variable time and our dependent variables. So let me double check myself. Yeah. And we also have a span, our initial guess. And then remember, we always use do for our method and then output true so we can evaluate our function at our times that we simulated. I already forgot. So our function, we have to do a lambda since our variables for the right-hand side. What am I doing? Our variables for the right-hand side or our parameters for the right-hand side, excuse me, were 3, time, height, and qin. So qin we have to specify. That's why we're doing lambda. So our vector, did I call it a vector? I called it a vector. Okay, cool. I'll just call it vector here. So vector, and then we have our right-hand side, and we specify our time, our vector of heights, and I think we do initial steady state, right? And we have to add our gain. That's what I always forget to do this when I was practicing. So we had our change right here, exactly what I use it for. So you need to make sure we're changing from steady state. It's the exact same scenario when I had a step change of 0 for our linear side. We need to have some sort of change in our system, so that's why we have a Q change. Hopefully that works. I think we have a time, so a time range. We already have that given from our simulation, so I just do 0 to that time, but remember this time is an array, so we have to splice it at the very last, or from the very last time point. I don't know how you want to say it. So that last value in that array, since it goes from 0 all the way to that last value. What else we got? I think it's just method redo and dense output, right? So method redo, so that's the most robust method we've been using. And then dense output true, so we can evaluate this at any time. We'll evaluate it at all the times, I believe. So let's see if this converges. Oh, y0, right, our initial guesses, right? So that's after time span. Right here. I'll do this. So y0, this will be our initial steady state guesses, I believe, right, for our vectors. So what did I call this? SS guess, right? I remember, well, no, that's a different thing. Yeah. No, this is not the guess. This is the, what am I doing? This is the initial values I'm putting in, right? Oh my goodness, what I'm doing. Yeah, initial states. So we solved that with our minimize. What did I call it? Thing? Yeah, initial steady state. Remember alternative, the root. We were able to converge that. We got the exact same thing. But minimize, I don't know, it's a little fancier. It's more powerful. So that's why we did it. And these are initial values. Is what I want to put here, not some guess. Confusing it with what we put in our actual minimize. Remember, we had to provide a guess to get our initial steady states. So where are we? Right here. Let's try it. Awesome. We got values. And now I'm going to evaluate this. Let's do result. Results and do I just put the result, keep it there. Then I'll do the solution, evaluate at our times, right? Yep, and that's all our changes in heights. Oh, see if this works. I don't actually remember this part very well on how I did last time. So I'll just do res.sol at t, and it's nonlinear. Oh, what the heck? They're same? Uh-oh, that's not good. I'm forgetting something. What am I forgetting? We have our change, right? 0 vector initial steady state plus acute change. Evaluated from time. Initial steady state solve from minimize. Results. No, it is not shown. Happen to you. As if, oh, I'm sorry. It's multiple arrays. So this is multiple heights. What am I doing? So if I do res.sol of that at t, but we want it at height 3. So we can either do 0, 1, 2 for, remember, index of what is happening. 0, 1, 2 for our third height, so it'd be 2 as we index it there. Because remember, if we evaluate it like so, we have 3 arrays. So these are corresponding to each height. So I'll just leave res here. So we have to evaluate this at the times, but we need to grab the third height. So I'll do -1. You could also put 2, should be the exact same. And now here's where the deviation variable is coming in. So I'll do 2 just to show you it's the same. And now we add back our, since we were in deviation variables, we add back our steady state. So h, where is it? 1. They're the same as what I use, right? Initials. And then this is an array, so I have to splice it. We can also do -1 or 2. It's the third tank. So this is our final value. So I'll also do 2. It's the same exact thing. That's it, honestly. Let's make this a little smaller. With 600? Other way around. Oh, here we go. Maybe. I'm getting so picky, man. Good enough. Whatever. Honestly, I could have just kept it. But yeah, these are the comparisons. You can see that our linear version versus our nonlinear version doesn't quite match up correctly. There's some changes there, and that's from the approximations made from the Taylor series expansion, that partial derivative, the Jax.Jacobian evaluated at our steady states. And that's why we had to add back our steady state for our linear function. So I believe that's all, honestly. 1 hour 21, not bad. I'm gonna go split this real quick. I think we hit everything for this problem. Did 3 tanks. I actually did the single tank too, so I could copy paste it. For my series, Jax.Jacobian. Yep, talked about that. State space A and B. How those matrices are essentially slopes of how the right hand side depends on either the state variables for matrix A or the input vectors for state, or input vectors for matrix B. And Sympy was our symbolic solution. So we did the transfer function. Once we did the transfer function once we did the Laplace transforms of those matrices, relating them to our I mean, it's just a Laplace transform, honestly. We took the Laplace transform and isolated the state variables and the input variables on opposite sides, and the transfer function was what was in between. It's what was being multiplied by our input function in the Laplace domain. So after we did that, we did a simulation for our linear side and use our solve IVP to evaluate at the same time span, and had a comparison here. So actually, what was what was it asking for? Compare the responses? Yeah, it's just less accurate, honestly. But now, since we have this transfer function, we can do stability analysis. Hopefully, is what I'm thinking we're doing after this. I'm not quite too sure, so don't quote me on that. But since we're done here, remember we had our deviation variable. Nonlinear didn't have to add that back since we didn't do any Laplace transforms, but we had to add it back for our linear since we did our Laplace transforms in terms of the deviation variable. So we added it back so it matches up with the same intercept. And yeah, there is a 1 convergence at this point in time, but for the rest, it's pretty far off. And you can imagine the longer this goes, there'll be a further difference where the nonlinearity reaches a steady state and linear has a different steady state. So I believe that's all I have. Again, if I don't open this up and unpause after this next pause. Just assume we're done. I'll leave it on this bit right here. Now scrolling, couldn't see I was on collab. So how about that? All right. Thanks for watching.